Thank you. So my name's Tony Staneff, and I'm the series editor of Power Maths, and also work for White Rose Maths, an organisation in the UK whose schemes of learning are used across the world. I'm looking forward to talking you through some of aspects of what I feel maths mastery is and what the research tells us. I'm conscious that schools will all be at different stages in their development of mastery, but hopefully there'll be something for everyone within here. So the broad aims that I want to look at today are this idea of belief and culture within schools, manipulatives and representations and the importance of them, the importance really of teaching for understanding, and then mathematical thinking as well, all key elements of what I believe to be effective teaching for mastery. So we'll take each section in turn, and as I said, if you've got any questions, we can take those right at the very end. So I think in order to teach for mastery, it has to start with the power of belief. It has to start with this understanding that all children can succeed in mathematics. And I've seen in too many schools, in too many places that I go in and support, I often find that there isn't that belief of every child, whether that's primary or secondary. We don't always have this belief that every child can succeed in mathematics. So why don't some students succeed in mathematics at the moment then? So firstly, I don't think we believe it as teachers. I think there's a teacher mindset issue. I don't think all pupils believe it, all students, all children believe it. We try to build on unsecure foundations. One of the key ideas of mastery is to make sure that those foundations are secure so children can build on secure foundations. There are gaps in knowledge when children arrive. So often children come into a year group, okay, or sometimes they arrive mid-year, and there are those existing gaps in knowledge. How can we plug those gaps? Pupils often only have a surface knowledge rather than a deeper understanding, and often in schools where examinations and assessment test that problem solving and deeper understanding, children who just have a surface knowledge really struggle with that. We often try and teach too much at once, okay, so why some students don't succeed is because they have cognitive overload and they don't have enough facts in long-term memory. Pupils are switched off sometimes and they don't want to learn. One of my arguments would be actually maybe it's to do with some of the other reasons why they're switched off. And behaviour of pupils, okay, is another reason that teachers cite. Again, I would say, is it behaviour, is something causing that behaviour from the list above? And then I think all this is to do with quality of teaching. So we study after study shows us that quality first teaching has a huge impact on what children learn and how effective teaching is really, how much they take away. So I think those are some of the reasons why students don't succeed in maths. And you've probably got your own, okay, if you can think in some pupils that you've worked with in the past, why they haven't been successful, but I think every child can be successful in mathematics. Here's a quote from Joe Bowler, and Joe Bowler talks about research that prompts educators to abandon the traditional fixed ideas of the brain and learning that currently fill schools. Ideas that children are smart or dumb, quick or slow. If brains can change in 3 weeks, imagine what can happen in a year of math class if students are given the right math materials and they receive positive messages about their potential and their ability. And so that is from Joe Bowler, who you probably all know as big with mathematical mindsets and the importance of this idea of a growth mindset in mathematics, that all children can succeed. And I think it has to start there. So if you want to take your mastery journey, it's vital that you start with this belief that every child can succeed in maths, no matter how much sometimes pupils do to convince you otherwise. So we have to start with that belief that every child can succeed in mathematics. And then we build on that. Just to give you an anecdote situation is that I went into a school last year and talked to the year 1 teacher, and the year 1 teacher right at the very start of the year was able to tell me where these children would be at the end of the year. And I said to her, how do you know that? How do you know that those children that you've highlighted will be there at the end of the year? Her response was, well, that's where they've come up from reception. That's where they've come up from early years. And so I know this is what they can do. So that's where they're going to be. And that's what's always happened. And so those children were probably at that place at the end of the year. But I think that's more of a self-fulfilling prophecy rather than actually what they're capable of. So you have to start. So underlying everything, my personal belief is that maths everyone can. Every child can succeed in mathematics. So it's important to build a culture in a classroom, department or school where teachers believe that every child can succeed in mathematics. Simple things like making sure when people come through the door into the staff room or into the department office that mindset is challenged. If some teachers come in and say, oh, so-and-so today just can't do it, etc., it's just adding a word like yet on there. So build that culture within a classroom department where you have this belief that every child can succeed. Have high expectations of all children. Sometimes I think we don't have expectations. Those lower attaining students, we don't have high enough expectations of those children, or potentially sometimes we give them work that they just can't do. They don't have the background knowledge at the moment, and then we infer that, oh, they're never going to be able to do it. Actually, they probably can't do it because they've just got a small gap in knowledge. And so therefore the final point is support children by building on what they know. So it's important that new learning is built on old learning, so you need to support children by building on what they already know. So first thing I would say is about belief. Next is CPA. CPA, for those that are not sure, stands for Concrete, Pictorial, Abstract Approach. Bruner talked about this. These three modes of representation: the inactive representation, the action-based, the manipulative stage of it, the iconic representation, which is more the pictorial stage, and then this symbolic representation around mathematical language, symbols, algebra, etc. Not just algebra, but numbers. So the importance of concrete, pictorial, abstract approach. So we, as White Rose Maths, as an organisation, we would encourage that children should use concrete manipulatives to help them understand the mathematics and help teachers teach specific mathematical concepts. Concrete objects and visual representations help provide an insight for children into increasingly sophisticated mathematics. And actually, you'll see later on that it's important that children understand really the maths that they're doing. Too many children can just do things, but they have no understanding, and that's just a shallow knowledge. What concrete objects do and visual representations is that they provide that understanding of what's going on. So everything from completing the square in secondary to understanding in primary multiplication through arrays. It helps you understand what's going on. As teachers, often people say to me, really, well, concrete objects don't have any impact and representations. It's vital that as a teacher you make the link explicit between the manipulative you're using, any representation then you then show, and the abstract. Don't expect children to make those links for themselves. You have to be clear that that counter there is representing that object there, and that counter is that number, because there are 5 counters, so it's a number 6. You are making those links explicitly clear, and you do that at all stages. Don't assume at any point that children can see that link until you make it explicitly clear. Concrete objects can be used with children of all ages and shouldn't just be reserved for children who are in early years or key stage 1 or first few years of their education. Make sure we're using concrete objects with children of all years, and there's plenty of examples where those are used that you can see. And then the other thing against you that teachers often come up with a reason why they can't use concrete objects is that they expect them to be able to use them straight away. You have to model carefully. You have to get them to use them, and you have to, they'll go wrong first. Right, expect that. And so so if I'm using place value counters for the first time, they're going to struggle using them. They're not going to see the link between maybe the base 10 and the counter that you're using. So make sure we're modeling it and that they're allowed to use it and allowed to get things wrong. Build time into your lesson for that. But the use of concrete manipulatives, research shows us that they have big impact on children's understanding of mathematics. And then there are 4 key elements of successful use of concrete and pictorial representations, and these are summarized as familiarity. Pupils know what the concrete objects are. Vividness, are actually having objects at disposal to use. In too many schools, they're tied away in a drawer, so you've got them in a drawer in the corner, and so we don't use them, and they're just brought out for children who struggle. And actually all children can use concrete objects and representations to help them understand more complicated mathematics. So I would encourage you to have those objects at disposal. The best schools, in my opinion, that I go around and see, have them in the center of the table, and children then use them as they need. I've already mentioned this one, but I can't stress it enough, making the alignment to the abstract clearer. At every stage, you need to link the concrete to the pictorial to the abstract. And then I've got an example here, a couple of examples, which we'll talk about in a second. So this first one, so children prior to this lesson were working with place value grids, and they had some place value counters that they're doing around. And then here is a visual representation of this that you can see. So, and then this helps children start to see why 4-digit plus 4-digit addition, and you can see then the abstract, the column, so you can see what's going on. So you can see in the right-hand column, the ones column, you can see that I've got 4 counters in the first number, that's the number 4 in the ones column, and you can see I've got 7 counters in the ones column for the second number. You can see that's the 7 abstractly, so you can see that, and then you can see what we're doing is that, right, what's happening here? So I've got 11 counters in total, but 10 of those counters, we've already done lots of work on grouping and exchanges, so I know that 10 of those counters can be exchanged for 110. We know 10 ones is 110, and so you can see really why then we end up with 1 counter and then we get an extra 10. Whereas if you just do the abstract calculation, the children understand actually what's going on. Does it make sense to them? And what happens is that concrete helps them, and the pictorial helps them understand the abstract mathematics. Here's an example from a bit further up in school. This is an equation, so we might have, so this is a very abstract concept, and I would encourage equations. You could introduce it through simple cups and counters, and then you might move on to the representation side to this, which is potentially a bar model. So here you can see about, so here we can see a bar model forming. So you can see here we've got 3a. And so we're trying to form this equation 3a plus 5. Our work on bar models already shows us that when we add in bar models, we add this extra bar to it. So I've got 3a is equal 3a plus 5. So children can see what 3a plus 5 looks like visually. And then we want to show that is equal to 17. So think about how we do that. So how do we show it's equal to 17? So we can draw a bar underneath with the number 17 in. How do we show they're equal? Well, those bars are the same length. That's how we show that that 3a plus 5 is equal to 17. So children can take quite an abstract equation and turn it into something pictorial, which will make more sense. But all the time you're making the link between the a's and the bars, the 5, the bar, the 17, why are they equal? You're making that link explicit. And then we can go about solving this, and children will then start, oh, I know what I can do now. Yeah, that's right. Okay, we can take 5 off each bar. So what does that look like in the calculation? Well, I can take 5 from both sides. So I'm left with 3a is equal to 12. And then because we've already used bar models before, okay, in an earlier year, we know that, all right, I know what to do here. I know that I'm going to share 12 equally between 3 parts. So in other words, I'm going to do 12 divided by 3, giving me an answer of a equals 4. So we can see that a equals 4. I hope those couple of examples show you the importance and how useful objects, concrete objects, and representations like the bar model are in helping children understand more complicated mathematics. And where schools use them, children show a greater understanding, which links nicely into teaching for understanding. One of the key things for maths mastery is ensuring that we're teaching children for understanding. In order to master something, you need to understand it. Often schools, teachers in schools that I go and support will often say they're teaching for understanding, but they're not. It's quite just do this, do this, do this. No, children don't have to do any thinking. So as we've just said, concrete objects and manipulatives will help children understand the maths they're doing, and therefore more likely to remember what they're doing, and also help them to problem solve. Think as a school how you could promote conceptual understanding. Really, so the examples that I've just given you promote conceptual understanding. You can start to understand how an equation is formed, what an equation looks like. That helps you understand that concept. Seeing and hearing lots of examples of a concept are useful for helping pupils to understand the core idea, and it's important and then that we draw connections across mathematical concepts as well. So in order to teach for understanding, we have to draw those connections from across mathematics concepts. I'll go into a bit more detail shortly. So procedural factual knowledge without conceptual knowledge is a shallow and ineffective and will lead to constantly having to remind pupils of how to do things. I think as teachers, one of the biggest questions I get asked by teachers is, children will come to my lesson, they'll be able to do it by the end of the lesson, and then tomorrow they'll come back to me and they'll have no idea what they're doing. In fact, some of them will say, I've never seen this before in my life. Right, so how on earth, and that shows just a shallow knowledge and a shallow understanding, really. You need to make sure you're promoting this idea of conceptual knowledge and this understanding of what's going on. Similar to the things that I talked about a few seconds ago, some of the examples, you need to make sure that we're showing what's going on because it will help children. So when children can't do 2 times 3 without using the fingers, do they know what 2 times 3 looks like as an array, for example? So it's vital that we teach for understanding and we show the meaning. The how needs a why. So it's not just explaining how to do something, it's about why this works. Why do you do it? And I think too often in schools want to improve their maths understanding, they don't ask enough why questions of the children. And so I'd encourage children to be questioned on why does that work? Why does this happen? Other ways that you can teach for understanding and try and help is use examples, make use of examples and non-examples as well. So too often in schools is that we just give, here's an example of it. What's an example not of it? What does it not look like? So if I was doing something as easy as easy as triangles, okay, what does a triangle look like? Is this a triangle that's if it's orientated a tiny bit differently? What about this shape with 4 sides? Is that a triangle? And this idea of examples and non-examples to try and children hone in on actually what the definition of a triangle is. The other thing that you can do to teach for understanding is talk through children's thinking and your own thinking, this idea of metacognition. So metacognition is where we understand more about our own learning and our own thinking, and one simple way of doing that is we talk through our thinking. So instead of just putting some work on a board, talk through that work as you're doing it. Talk through the thinking that's going on in your head. A bit like when I was doing the example of the bar model, at every single stage I talked through my thinking. That talking through the thinking helped you or the children understand it more. So talk through the thinking, that will help. So the goal of a teacher, so if you're trying to teach for mastery, should be to get students to think about the meaning. As teachers, we must design lessons that will ensure students think about meaning of material. Making maths meaningful is a proven strategy also to improve engagement. So if children understand something, they're more likely to be engaged with it. It's when there's not the why with it that they think why, then they start asking the questions. I'm not sure where that comes from. And I don't think it's always acceptable. You say, yeah, well, this is what you do. This is how you do it. Just do it. Just do it. That doesn't help children retain information. Try and explain to them why the answer is as it is. And things like representations and manipulatives can help. Here's just a few examples from, I've taken them from Power Maths, a textbook series, to try and help a bit of an understanding of the why. So why is 3/8 equal to 24, for example? So we can see what 3/8 is. We can see that y is division, the same as repeated subtraction. So what we had 24 plant pots. We're putting them into groups of 4, and then you can start to see, well, once I've got one group of 4, that's another group of 4, and you can start to see that's why it's the same as repeated subtraction. And then why is 3 multiplied by 4 double 3 times 2, and why is 3/8 double 3/4? And again, the images, that conceptual understanding, will help you see help children understand. So therefore, try and use that. Try and bring out the meaning of the maths. It will, I promise you, will help children understand the math more, and they'll retain far more. Other things that you can do is adopt a curriculum for understanding. So Rosenshine talks a tiny bit about this. If the conceptual knowledge and understanding will make pupils better problem solvers, then you need to choose a curriculum model that helps build conceptual understanding. Research shows across jurisdictions where children have a greater conceptual knowledge, their curriculum plans study fewer topics in each year so they can do them in more depth, and they break topics into smaller steps. In other words, the mental distance between topics are quite small. So teaching for understanding is vital. So very quick recap. So we talked about its importance of culture, how we have to build this culture of every child can succeed in mathematics, even though sometimes they try and convince you they can't. Then we have to make sure we're using the right equipment and the right manipulatives to help us teach for understanding. And teaching for understanding, the why, not just the how you do something, is essential to teaching for mastery. So I then want to move into thinking next. So this is a quote from Daniel Willingham. So people are naturally curious, but we are not naturally good thinkers. Unless the cognitive conditions are right, we will avoid thinking, Willingham says. So the idea of this is that we learn things, we're often open to new ideas when we're curious. And as primary and even secondary school teachers, we can make maths curious. I think often maths is a subject where we don't make curious enough. And there is so many ways that we can make it more, oh, what's going on here? What's happening there? As opposed to just going in with, right, today we're doing 3-digit addition plus 3-digit addition. How can we make it a bit curious? So again, I've just taken a few examples. So this is a lesson that is to do with, for example, where objects lie. And you might want to make use of image helps make children, helps get that curiosity across. So quite a vivid image. Here are just a few vivid images that might make lessons a bit more curious. This could be a shelf in the classroom. It doesn't have to be an image. It could be a shelf in the classroom with a toy in it with some books on it. And then the children can start talking about it. Here's some children. Here's a child in a chocolate shop. Really? Okay. What? Bring it to life. Okay. Make it curious. Tell them a story. What does it make them think about? What could the questions be? Get them into it. Make it curious. Okay. Whatever it is. Maybe they come into a classroom and there's a lot of litter all over the classroom. Oh, what are we doing today? And maybe it's about, right, we're picking them up in tens. There's lots of things that you could do to try and build that curiosity, because we will, as humans, as children, we will explore things. We're more likely to explore things if we're naturally curious about them. So just a tiny bit about the brain. So the brain is not designed for thinking and is actually not very good at thinking. However, we do enjoy mental work. I mean, we wouldn't be teachers now if we didn't enjoy mental work. However, if a problem or task is too difficult for a pupil, what happens? Well, children will often switch off, right? And all it come out in behavior ways. And so therefore, that's often a sign it's too difficult. It's often a sign sometimes it's too easy. In other words, okay, just do these. And then some children will also switch off as well. How do we get through each day doing all the things that we do? Well, the answer is memory. Right, so we rely far more on our memory than on our thinking system. So using memory does not use up much of your attention. So we don't really like thinking, okay? We're not actually very good at it, but sorry, our brain's not designed for thinking. We're not very good at it, but we do enjoy mental work, providing the cognitive conditions are right. So here again is Daniel Willingham from his book, Why Students Don't Like School. This is an example of what he presents as a simplified version of what's going on. So imagine children in a classroom now. So the environment is all the questions that you're asking the children to do, all the things that you're doing. Working memory is what's going on in your head at the moment. So think about those things that you're thinking about. Are you thinking about what I'm saying now? Are you thinking about something else? Are you thinking about this? Are you thinking about that? That's what's going on at the moment. And then long-term memory is that vast storehouse of things in your head that you've got no idea resides there until somebody asks you to bring it out. What colour's a polar bear, for example, okay? And it comes out and it'll be into your working memory. And it took very little effort to get into that. Thinking happens when you combine things from the environment, so the problems that you ask children to do, with things from your long-term memory in new ways. And this combining happens in working memory. So thinking is when you combine things from the environment, so the questions you're asking, with things in long-term memory. That's why it's vital that we've got things in long-term memory. Children, to understand, to be able to be successful, have to have facts and procedures in long-term memory. So here's a simple maths question: 15 multiplied by 7. Give you a few seconds to work it out. And then think about the things that you had to know in order to work that out. So hopefully we all got 105. And then how did we get 105? Well, we had to know that 10 partitioned 15 into 10 and 5, and then we maybe did 10 times 7, and then 5 times 7, put them together. So you needed to know facts, you needed to know procedures. People may have done it a different way. Having appropriate procedures stored in your long-term memory helps a great deal when you're thinking. That's why it's easier to solve this problem than some of the other ones. Often the information provided in the environment is not sufficient to solve a problem, and you need to supplement it with information from long-term memory. What's vital is that I want you to try and imagine a child who didn't have any facts or any procedure in their long-term memory to be able to do that. They would struggle, and that's why children struggle, because they don't have that information in their long-term memory. So now we're talking about memory. Let's just very, very briefly just go into a tiny bit more detail about memory. So it's very mysterious. We can lose a memory created 15 seconds earlier, but then there are seemingly trivial things in our heads that have lasted for a lifetime. So your memory system is essentially, Daniel Willingham says, that if you have to think about something carefully, you'll probably have to think about it again, and so it should be stored. And cognitive scientists agree with this. So the idea is that your memory is not a product of what you try and remember, it's actually a product of what you've carefully thought about. And I think too often in schools who want to teach for mastery is that we don't get children to do enough mathematical thinking, enough thinking, right? Because I just told you they don't like thinking. We don't like thinking. But in order to get things into long-term memory, we have to think. So therefore, we've got to set up the conditions right to make sure those children are ready for thinking, those cognitive conditions. So your memory system says that if you have to think about something carefully, you'll probably have to think about it again. So I'm based in England, and so in places like the UK, the majority of teachers of mathematics that I work with on our teacher training often start by planning what they want their students to do. If you look at some of the highest performing jurisdictions, teachers of mathematics design their lessons by planning what they want their students to think about. And I think that's a key difference. Are we going to do this today? No, hang on a minute. I want children to think about which of the two sides in an isosceles triangle, which of the two angles in an isosceles triangle are the two equal ones if those are the two sides that are equal. And that might be, and I want them to think about that, and I'm going to plan what I want children to think about, and therefore I'm going to plan the activities around that so to make sure they think about that. So the underlying teaching and learning principle is that to be the most effective teacher you should pay careful attention to what a task or piece of work you will set actually makes students think about, not what you hope they will think about, because what they will think about is what they will remember. And I can't stress that enough. Really, the importance of mathematical or any mathematical thinking within a lesson is vital, because it's that's going to help you get over this issue if you've got it with any of your groups where children say, oh, I don't remember how to do it, I can't, I forgot it. By carefully getting them to carefully think, they're more likely to remember it. I'm not saying 100% they're going to remember it, but they're more likely to remember it if you can get them to start thinking about what they're doing. So here's an example of a few questions from a typical, what I call a typical UK textbook. Take a few seconds to have a think about them. So what do you notice? Well, what I notice is that once you've done the first couple, you really stop thinking about what you have to do. What the teacher probably wants them to do is realize that if the denominator is equal, then you can add the numerators together, right? So the idea that if the denominator is equal, then you can add the numerators together. So that's what I think what the teacher wants them to understand and to think about. So they go through this 1/3 plus 1/3 is 2/6. Sorry, 2/3, apologies, sorry. 5/6 plus 5/6 is 10/6, okay, etc., etc. They probably get to question 3 and they stop thinking about that, and they just add up the top numbers. They don't start to think about really that 3/10 and 3/10, oh yeah, the denominators are the same, so I'm going to just add the numerators. They don't think that. Maybe they start thinking when they get to question 8, oh, what do I do if I've got 3 fractions? And then maybe on question 9, what do you do if it's a subtraction? So those are all things that, but largely, I don't think they're thinking about what you want them to think about. Let's look at an example from a different textbook. So adding and subtracting, like fractions this time, with what I would call some step thinking, a bit of variation, intelligent practice. So question 1, very similar to the last one. 3/8 plus 2/8, 5/8. 2/9 plus 6/9, 8/9. And then straight away I've now got I've mixed in the subtraction a bit earlier. So children have to start thinking, oh, do I do the same? Yeah, the denominator is the same again. Then on question 4, what am I thinking about here? So that's further step in thinking. So, oh, I've got 11/11ths, and what does, oh, that's equal to 1. And then, oh, look in question 5, I now have to use that to help me work out this one. So, all right, so I know 11th letter. So what? So again, there's that step thinking taking place. Number 6, then, why do children maybe have to think about number 6? Well, it's because can the answer be 0? 5 27ths plus 8 27ths equals to 13. 27ths minus 13. 27ths gives you 0. 27th. Again, at all stages in this exercise, children will be thinking far more about the denominators when they're equal, what you do. Number 7, another example, 8. What will children be thinking about in number 8? So you can see the difference between this exercise and the one previous to it. This one, the questions in here are far more, get children to think far more. If you just give children lots and lots of questions that are repetitive, they stop thinking about what they're doing and the understanding, and they just end up doing. And your job as a teacher is to get children to think about the maths that they're doing more. So it's how can we design lessons, how can we design questions to help them with that thinking. So, in summary, this is what I believe. I could talk about so many more things, I should say, as well, but these are the things that I've put down are essential to building this, what I'd call a road to success with teaching for math mastery. So believe that every child can succeed in mathematics. Follow a small steps curriculum plan, which has been designed to have a small mental distance between topics. Always teach for understanding, right? You want to develop the factual and procedural fluency, but you need to make sure that you're teaching that alongside teaching for understanding. Don't teach just the how, but teach the why. Teach them in tandem. Ensure that all pupils are thinking in your lessons. And I'm sure you can all think of simple strategies. You all know them, simple Kagan strategies, simple mini whiteboards, all those things that get all children thinking, because it's thinking that's going to lead to learning. Avoid doing the work for the pupils as well. Avoid doing all the work, all the thinking for children. Curiosity, remember, is what prompts us to explore new ideas. What's that hook? What's going to get them into the lesson? Give them things to explore. Understand as well the importance of that concrete pictorial abstract approach, because it will help them develop that conceptual understanding. And you need to also respect the cognitive science and the brain's limits. So we talked briefly about those, about working memory and long-term memory, about how the brain works and how we need to have so many things. We need to draw things from long-term memory into working memory. But then remember, working memory's only got a fixed number of slots, and we can't put too much into working memory before we have this idea of cognitive overload. So that's a summary of the things that I've discussed today. And I think that's a good starting point for any people who are starting to take a journey into mastery. Or if you're on your journey, there's a few more things there that you can start to think about. Go around your classrooms, have a look at what's working well, what's not working well. So thank you for listening. and I don't know if there are any questions.
Okay, thank you so much, Tony, and thanks to everybody that's registered and attended. We hope you found the webinar useful. We'll stay on the line just a couple more minutes, so if you've got any questions for Tony, then just pop them in the chat box and we'll ask Tony. We have had a couple of questions about the link to the recording being sent out, so we will send that out to everyone that's registered over email in the next couple of days, and then it will be on our website as well. So we'll let you all know. So Tony, we've got a couple of questions. We've got, how can we apply this for 25 students?
Could you just ask that again? Sorry, apologies.
We've had a question about how we can apply this for 25 students.
In a class?
Yes, possibly in class, yeah. A small school.
Is there anything? Oh, just you mean you mean it's across it's 25 students across all the age range?
Yeah, I would have thought so. Just a small school.
Okay, so I would say there are some things that I think you can do. Firstly, the first one around building a belief, this idea of a growth mindset in mathematics across the school. So I think it's really important that there's a shared understanding of what that everybody can succeed in mathematics. That's the first thing I would say, right? The second thing I would say is that it's important that you know the progression. You need to make sure that you've got a progression, so you know what builds on what, so that then if you've got 25 children, I'm sure you will have an understanding of actually where each of I'm sure you'll have a better understanding where each of those children are and where their gaps may be, what information they need. And then I think it's about, right, that's where they are at the moment, and then how can I build on that given our plans that we've got, really. But I think all the rest of, so any time that you introduce a topic, it's important to teach for understanding. I think, is there any way that children can work collaboratively together, for example? So could you put pairs of children together whose skills complement each other and knowledge complements each other? That's potentially, that could be something that could be done. Yeah, but I think all the other things can still apply, really, even within a small school.
Lovely, thank you. We've also had another question about how we can apply this to students with special needs, i.e. dyslexia and dyscalculia. Yeah,
great question. Yeah, great question. So I feel that again, children who I don't want to just give it the same answer that I've just given, but I think very similar. I think it's recognizing where children are at the moment. So it's recognize actually what their cognitive limits are, and then it's about building on what children already know. And I know that's really difficult in a classroom environment if there's several of them in the same room, but maybe try and scaffold sometimes, maybe try and make sure that you build up their so you're not making too big a steps in their cognitive jumps, okay, so that their thinking is too big. We're trying to make sure we avoid that. And I would say also that the CPA approach will help them really, so they can develop that understanding. I think that respect where they are at the moment, and right, what's the next thing I need to do to be able to build it, because I think children with dyslexia, dyscalculia, I think each of them are different, and I think it's recognizing that they're different, but all of this can apply to those as well. Yeah.
Thank you. We've got a question about, what if some students have short attention span, or they're forgetful and always forget to bring their textbook or worksheets?
Okay, so then I would firstly potentially, I don't know if the school's got a policy on that. So, for example, if they don't have a policy, is this something that could be done as a policy? So that's the first thing I would say. But then, if, for example, they haven't brought the textbook and they need it, is there any way that you could, for example, talk about so we often talk about sometimes pre-learning, so where children maybe the lesson before could they could just briefly look through, okay, this is what we're going to do tomorrow, and you're not doing the lesson, but one of the things that you could do is go through that very briefly, and so that expresses the importance of making sure that they need the textbook for the next lesson. It gives them an understanding of where they're going. On the short attention span, again, I think I would encourage thinking about, right, what's the hook, what's going to get them into it, and then chunking, not just chunking, but children working together. So if you maybe take something like the I do, we do, you do approach, okay, that's always a good approach, where the teacher models something and then maybe they work in a group on a short activity that builds on what the teacher's done, then maybe they work in a pair for the next one, and then maybe they work individually. So it just chunks it up, really. That's a potential how you might help with a short attention span.
Yep. We've had a question on assessment. Are there assessment tools that you can recommend or have had experience with that support this type of learning?
Yeah, so as White Rose Maths, clearly we've created some assessments and also some end of unit materials as well, which could be used. Okay, so whether and you don't have to be following the curriculum, the White Rose Maths curriculum. There, you could just take some of those questions that you could. So in other words, you're building in that retrieval practice, etc. I think those are things that people could look at. But that's the best. Yeah, I think one option is to develop it as a depending on how big the school is or cluster of schools. I don't have any right. This is beyond the White Rose Math stuff that we've done, which is quite extensive, and it's out there for people to use, which they can download from the website. There's a lot there that they can tailor if they're doing it in a slightly different order. That's something that they can do.
Okay, and we've had a question about pictorial approach.
Yeah.
I know the pictorial approach plays a major role in children's thinking, but how can we challenge children's thinking without using the pictorial approach?
Well, I think so. I think that the challenge is really, it depends where a child is, really. So if a child, I wouldn't encourage, if a child doesn't need a pictorial, if a child understands the maths that's going on because they've gone through that approach, then I don't see any issue why children should be eternally dependent on, say, the bar model or anything. I think the bar model helps children see the underlying maths of a question, and I think if you present two questions together and show which is similar structure, that will help children, and therefore if they get presented with that in the future, they might not need a bar model, or they might not need this. What I would say is that it depends where a child is on their journey of understanding. Some children may need a bar model to answer it. Some children may be comfortable using eventually an abstract form. But as long as those children who are not using say a pictorial approach, as long as those children are able to explain why something's happening, I think that's absolutely fine. I think it's the why that's the bit. It's not just, oh, this is what you do. It's making sure that those children understand why.
Okay, and we've had a question about Power Maths being included in the specification of iPrimary, the Edexcel iPrimary series. I believe the answer is yes, but I think that you've got Alex there with you, Tony. So I think Alex will be able to give us a brief yes or no, if Alex knows it.
Could you repeat that question?
Is Power Maths part of the Pearson Edexcel iPrimary specifications?
We're currently looking at the alignment to that programme, so we'll hopefully have a bit more information on that over the next few months.
Lovely. Okay, thank you, Alex.
That's all right.
We've had a question on, should this CPA approach also be included when assessing, i.e. during exams, and also the manipulatives provided during exam periods?
Great question. I'm going to sit on the fence on this one a tiny bit. I would say it depends what the purpose of the assessment is. So if you want to check whether children can do it without using manipulatives, and then then fine, okay, then that will help you understand whether children are fluent in it now and can reason problem solve with it. However, if the purpose of the assessment is to check where children are, and so actually do they still need to use this, then I think that's fine. And then I think the teacher it's how then the teacher uses it to help them make a judgment. So if I go back to the pictorial side, the bar model, for example, you might want to give children a problem where they don't need to necessarily use the bar model, or you don't give them they might need to use the bar model, but you don't give them an image of one, and then see whether they use one, and then compare children who have used one to those that have not. So I think children should be allowed to use them if they need them, if they're at the stage where they still need them, because there's no point in doing an assessment for you to tell you that they just can't. If they can't do it, then if you already know they can't do it, then allow them to use it so that then at least they feel some sort of success. But if you want to check whether they can do it without it, then I wouldn't give them it.
Yeah. Okay, I've had a question from Sarah, and hopefully I'm asking this question correctly, Sarah. So she has, how can we use these tools with advanced math concepts, and how can we change our preparation from what they need to learn to how they think, especially with new concepts?
What do advanced concepts? So could you just repeat the start of the question again?
How can we use these tools with advanced math concepts?
So depends how advanced we want to talk about. So whether it's solving equations, for example, I think these right up to even if you went into secondary and you started looking at I don't know, some of the geometric series through by looking at an image of squares that go to infinity. There's so many images in maths can help draw out that understanding. Yeah, and I think there's lots of sources on the internet, information I'm sure you can find around really. Algebra tiles, for example, could be key on helping understand more complicated mathematics. Multi-link cubes to understand maybe sequences. There is so much. Yeah, I feel that they will help children develop that mathematical thinking. If, for example, they do have some algebra tiles and then they use it to do an expansion, they can see how that links. For example, in primary, you might use base 10 to do a 2-digit by 2-digit multiplication, and so they can start to see. When I talk about drawing links across, it all starts to help them see the links of maths coming together, really. So I think you can do it. I think it just takes more thinking about, really.
Lovely. And we haven't got any more questions, but we've got a recommendation from Glenn Davis, who says that teachers explore the work of Carol Ann Tomlinson on differentiation. So thank you for that, Glenn. So we haven't got any more questions. If anyone else has any quick burning questions, we can go about 5 more minutes. But if not, we can thank Tony for his time.
Thank you. Thank you, everyone.
Lots of people are saying thank you, Tony. Oh, we've had a quick question saying many students do not like my writing steps. Any suggestions?
Writing steps.
What's your quick fire writing suggestions, Tony?
About writing steps, and what they mean for writing, or is in the steps for writing a method for a maths concept? Do we know any more information?
Don't know any more. No.
Yeah.
I'm
not sure. Sorry.
That's okay. Okay, we've had lots of thank yous. Very useful, very informative. Lovely. So we'll send the link round to everyone afterwards, and if you have any more questions, then just email us, and I'm sure Tony will gladly answer any more questions offline. Lovely. Okay, thank you all very much.
Thank you. Thanks, guys.
Thank you.